Okay, well, I can see we just hit 1 minute after the hour, so we're going to go ahead and get started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of today's talk to take questions. We have a designated Q&A portion. So in the meantime, please just do your best to make sure your microphone is muted and your video camera is off when you're not intending to speak. Katie, thank you so much for introducing today's speaker.
Thanks, Matt. I'm Katie Barnhart, also part of the Landslide Hazards Program here in Golden, and it is my distinct pleasure to introduce Alex Gore, today's speaker. So Alex received his bachelor's in geological sciences from the University of South Carolina and is presently pursuing a PhD in geosciences from the University of Arizona. I have had the benefit of working with Alex in the field, where he has used his skills from pole vaulting to show me how to do a mini disc measurement very effectively on steep slopes, and also has transferred from past experience carrying LiDAR equipment through one form of mud to mapping mud here, debris flows as is shown in burn landscapes of the southwestern US. I think you're in for a treat because Alex is really quite adept at bridging the sort of detailed field measurements and applicability of modeling to this really important topic of post-fire debris flow hazard assessment.
Yeah, thank you, Katie. As she said, I am Alex Gore. I'm a PhD candidate at the University of Arizona, studying post-wildfire debris flows with my advisor, Luke McGuire. And today I'd like to talk to you about a reduced complexity debris flow runout model that we've developed called ProDF with our colleagues Ann Uberg at the Arizona Geological Survey and Francis Rengers at the US Geological Survey. So I'd like to talk to you about our runout model today. And just off the top, we found that this model is applicable in both burned and unburned landscapes, but we found that it is particularly adept for the use of rapid hazard assessment following wildfire. So today I'm going to focus on applying the model in post-wildfire scenarios. So a brief overview of my talk, I'd first like to outline the model itself, ProDF. I'll discuss what components make up the model, what inputs are required to run a simulation, and then what outputs are generated by ProDF. I will talk about this in the context of several different post-wildfire debris flow inundation scenarios. So the 2018 Montecito debris flows in Southern California, as well as the 2021 Flag Fire and 2022 Pipeline Fire debris flows from Northern Arizona. And with that, we'll see that there are some differences in post-wildfire debris flows in these different settings, and we'll talk a little bit about how some model parameters as well as input volume influence model output in different settings. But before we get to that, I'd first like to talk about post-wildfire debris flows themselves. So I'm sure many in this room are familiar with the phenomenon, but for those who aren't, debris flows are fast-moving mixtures of water and sediment that occur in mountainous regions around the world. However, they are particularly prevalent on steep slopes that have been recently burned by wildfire. One reason is that wildfire reduces vegetation cover, so the amount of canopy that's available to intercept rainfall is reduced, so we get more rain making contact with the soil surface and eroding material by rain splash. We also see that wildfires tend to alter soil hydraulic properties. It's not uncommon for us to see that wildfires reduce infiltration capacity in burned soils. So because of that, we will see more rainfall running off the surface, generating overland flow, as opposed to infiltrating into the soil following wildfire. Now, this flow goes over the surface and entrains sediment, and over time mobilizes into a debris flow. And so this is a mechanism called runoff-generated debris flows, and they are the predominant debris flows that occur in burned settings. They don't have a distinct initiation zone, as you might see in a debris flow that's generated by shallow landslides or the fire hose effect. And I have here a video of a runoff-generated debris flow that occurred on a burn slope following the 2018 Buzzard Fire in western New Mexico. So you can see here, shortly after rain begins, we get runoff, and then pretty quickly we get several large pulses of post-wildfire debris flows. Fortunately, this debris flow occurred in a pretty remote watershed in the Gila National Forest in western New Mexico, and there were minimal impacts to downstream infrastructures from this event. But you can imagine how if an event like this or of a larger magnitude occurred in a more urban environment, how that could have some pretty strong impacts to downstream communities. One region of the western United States that has a well-documented history of pretty frequent post-wildfire debris flows is Southern California. A recent study found that there's a post-wildfire debris flow of some magnitude virtually every year in Southern California, and a little less frequently, but still about once a decade, you get these large events that have some pretty dire consequences to downstream communities. So this is an example of one such debris flow. So these are the 2018 Montecito debris flows that initiated following the 2017 Thomas Fire. And as a result of this event, over 400 homes were damaged, with several of those being swept from their foundation. And unfortunately, 23 people passed away and 180 more were injured as the result of these flows. So Southern California, one region of the Western United States that has a pretty long, well-documented history of post-wildfire debris flows. However, other regions of the Western United States don't have as well-documented of a history of post-wildfire debris flows. And one region is the southwestern United States. And so when I refer to the Southwest, I'm talking of the states Arizona and New Mexico. Forests in these regions are burning more frequently and at higher severity recently than in decades past. And as a result, they are becoming more susceptible to post-wildfire debris flows. And then at the same time, the wildland-urban interface, or the area where the built environment interacts with or is adjacent to areas of wildland vegetation, is growing. Arizona has one of the fastest growing wildland-urban interfaces in the country. So the result is, as fires frequency and intensity are increasing along with population growth, you're getting more people put at risk to the hazards associated with post-wildfire debris flows in the Southwest than ever before. So we have here two examples from debris flows that occurred in northern Arizona in the past couple of years. So on the left, we can see a structure that was damaged by a debris flow that occurred following the 2021 Flag Fire just outside of Kingman, Arizona. And then on the right, we can see a property that was impacted by a post-wildfire debris flows following the 2022 Pipeline Fire. So while this region doesn't have the long, frequent, well-documented history of post-wildfire debris flows like Southern California, we are seeing an increase of debris flows that are impacting downstream infrastructure in other regions of the Western United States. So the long history of debris flows in Southern California, coupled with kind of this uptick in impactful debris flows in the Southwest, really underscores the necessity for having a well-established framework in place that can be used to estimate the potential impacts of post-wildfire debris flows. And so when we're thinking what we want to know about these events before they happen, we have several motivating questions that we can think about. So we might want to think, how likely is it that a debris flow will occur in a burned watershed in the years following wildfire? We also might consider how large that debris flow will be. So, larger volumes have the ability to inundate more areas. So we might consider the magnitude of a post-wildfire debris flow. And then we might also want to consider how far will that debris flow go and who will it influence or impact downstream. So these are three big picture motivating questions that we might want to consider when establishing a hazard assessment framework. Now, currently, we have well-established methods to address those first two questions. So how likely? We have an established debris flow likelihood model introduced by Staley and others in 2017 that can be used to predict the occurrence of a post-wildfire debris flow in a given watershed. And we can generate maps like the one we see here on the left. So watersheds with darker shades of red are more likely to produce a debris flow given a certain rainfall. We also have the ability to answer how big is that debris flow going to be. So the Gartner et al. 2014 emergency assessment model is used by existing hazard assessment frameworks to predict how much sediment will be deposited at the outlet of a watershed outlet given or within 2 years following wildfire. And so we see that this model, which I'll talk about a little bit later in the talk, I think I might have heard someone if someone has their mic off or on. But this model considers watershed relief, area burned at moderate and high severity, as well as peak I-15, or the rainfall intensity measured over a 15-minute duration. So we have well-established methods that can be used to answer how likely is a debris flow to occur and how large will it be, but we lack an established method that is frequently used in hazard assessment frameworks to predict how far will that debris flow go and who will it impact downstream. Now, there's a couple reasons why we are lacking a debris flow runout model in these frameworks. And one is that a lot of existing or well-established runout models are pretty computationally expensive. We have a lot of established physically based models that try to replicate the complex interaction between the fluid and solid component of a debris flow. But these models are often computationally expensive, and they're not applicable for modeling debris flow runout on a regional scale where you might have 10, 100, or even 1,000 watersheds that may produce a debris flow following wildfire. Existing empirical runout models often contain or require detailed parameters that can be difficult to constrain, especially given the short time frame between the end of fire season and the onset of the rainy season. So in Southern California, there's often only a month or two between when fire season ends and when the rainy season begins. That is not even the case in every scenario. For example, the Montecito debris flows, which occurred in January of 2018, were triggered by a rainfall event while the Thomas Fire was still burning. This phenomenon is also common in the southwestern United States, where peak fire season overlaps with the onset of the North American monsoon. So what we see is that frequently the same rainstorms that contain the wildfire are the same that produce post-wildfire debris flows. So it's really important to have a computationally efficient model that requires relatively few parameters to have the potential to implement that into a hazard assessment framework. So for that purpose, we proposed the Progressive Debris Flow Routing and Inundation Model, or ProDF for short. So ProDF is a reduced complexity inundation model that we have found to be computationally efficient and requires only a couple of parameters. The first part of my talk here is going to be outlining the components of ProDF and the inputs and the outputs generated by the model. But if you're interested in learning more about the methodology and really getting into the details of the model and how it performs, I recommend this publication that just came out earlier this year that we published outlining the methodology behind ProDF. But before I get into the model components, I just want to reiterate that I will be explaining model development through the lens of the 2018 Montecito debris flows. So I already mentioned a little bit of background about these events, but I want to add that in the days following the events, a team of scientists from the USGS traveled to Southern California and got really detailed information regarding debris flow volume, peak flow depths, and the extent of inundation. So these hashed polygons to the right are the observed extent of inundation for 5 debris flow producing watersheds. And so these 5 debris flows, heavily impacted the downstream community of Montecito, California. So as we kind of step through the model description, I will be referring a lot to this event and to these mapped extents of inundation. So ProDF itself is composed of 2 parts. The first is a series of empirical equations for debris flows introduced by Rickenman in 1999. So ProDF routes an input volume downstream and calculates the flow depth at every point in a model domain until a certain stopping criteria is met. So here are the 3 most important equations that are implemented in ProDF. So the first relates peak debris flow discharge to the input volume, which is M, using empirical coefficients that were calculated by Rickenman in 1999. Then using a series of relationships that relate debris flow discharge to velocity and channel width and depth, we can derive this second equation here. So this calculates flow depth as a function of debris flow discharge, channel width, the flow mobility coefficient introduced in Rickenmann, and topographic slope. So the model calculates a flow depth at every cell on the landscape using this relationship here. And as volume is routed downstream and depth is calculated, it is not routed indefinitely. We have a stopping criteria built in to ProDF. And so prior to the start of a simulation, a user will prescribe a yield strength, shown here as tau sub y. At every point that flow is occurring, similar to calculating depth, ProDF also calculates a shear stress, showing calculated here in equation 3, considers density, gravity, topographic slope, and flow depth. So at every point where the shear stress exceeds the prescribed yield strength, flow will be routed. But where the yield strength exceeds the shear stress, the flow will stop being routed. So these are the main empirical equations that the model utilizes. I've mentioned a few times that volume is routed, but how do we route it? Well, we use a progressive variation of the multiple flow direction algorithm. So the multiple flow direction algorithm routes flow from one cell to all downstream neighboring cells weighted by slope. However, the multiple flow direction algorithm is best suited for low flow conditions because it only considers topographic slope and not the depth of the flow. As a result, when you have floods or debris flows where the flow depth exceeds the depth of the channel, you're going to get scenarios where the flow is artificially contained to the channel despite being deeper than the depth of the channel. So to address this problem and to more accurately capture the lateral movement of debris flows when they overtop the channel, we used an iterative variation of the multiple flow direction algorithm introduced by Pelletier in 2008. And this allows us to accurately capture areas where the flow overtops the channel. So the way that works is that prior to a simulation, a user will set a number of iterations. So this can be any value set by the user, but for this example, as well as all others that I showed through this presentation, we use a value of 100. So I'll be referring to the value 100. So that is the number of iterations. So at the start of the first iteration, the volume is routed downstream using the traditional multiple flow direction algorithm. And this will kind of identify low flow pathways. However, at the end of this iteration, 1/100th, or 1 over whatever number of iterations you prescribe, of the flow depth is added to the original topography. So this creates an updated flow routing surface. So at the start of the second iteration, you will route the flow over the original topography plus that fraction of flow depth. And then the same process will occur over and over again until you reach that 100th iteration. So we can see here on the right an example from San Ysidro Creek, which is one of the 5 watersheds that produce debris flows upstream of Montecito, California. We see that early on in the simulation, iteration numbers in cooler color, so dark blue, we see that the flow is contained to the main channel to the right of that flow path. But we see as the simulation progresses and we get to iteration 25, 50, 75, we see that the flow begins to overtop the main channel and move laterally, particularly at kind of the midpoint of the flow and the downstream extent. And then very late in the iteration, in the simulation, we see that the flow spills into a distributary. So we can look at this in a cross-sectional view from that transect from A to A prime, right above where the flow splits into that main channel and the distributary. And we see the same phenomenon in a different perspective. So we see once again early on in the simulation, roughly iterations 1 through 50, the cooler colors, we see that the flow is confined to the main channel. However, as we progress through the simulation, the flow begins to overtop and move laterally and eventually spill into the distributary. So ProDF is composed of a series of empirical relationships derived for debris flows coupled with this progressive flow routing algorithm. Now that we have a little bit of a better understanding about how ProDF works, let's talk about the inputs that are required to run a simulation. So ProDF requires only a handful of inputs, the first being pre-event topography. So this is an example of the pre-event topography from the Montecito study area. ProDF just takes the pre-event topography as a text file, and this can be, any resolution. Model performance is typically better at finer resolutions, but we have used the model on resolutions as coarse as 10 meters. This is an example of a 5-meter resolution DEM. Second, the model requires starting points for the debris flows. So this is not necessarily the same as an initiation point. As I mentioned earlier, most post-wildfire debris flows are runoff generated and lack a defined initiation point anyways. So this just needs to be located anywhere upstream of where you expect inundation to occur. For our scenario at Montecito, we simply use the upstream extent of our pre-event topography as the starting points. But if you have topography that extends into the upstream stretches of your watershed, you can start the model anywhere upstream of where you expect inundation to occur, and that will not affect the runout. Third, you need to prescribe input debris flow volumes. Like I mentioned earlier, detailed information regarding the volumes of all 5 of these flows were gathered in the days following the event. So we had pretty well constrained input volumes for this scenario. And we can see the values for these 5 watersheds shown here. However, if you don't have a well-constrained volume, which a lot of times it's difficult to have, especially if you're using it in a predictive sense, you need to come up with another way to set an input volume. So one commonly used way is to prescribe the emergency assessment Gartner model for debris flow volume, but you need to provide an input volume to run a simulation. And then finally, you need to define values for 3 flow mobility parameters: the density of the flow resistance coefficient, which is a viscosity-like term introduced in Rickenman, who derived the empirical relationships, and then the yield strength. So these 3 values influence how the flow acts. For example, yield strength plays a big role in flow mobility. Like I mentioned earlier, the yield strength is used for a stopping criteria. So the higher yield strength you have, the higher the shear stress at the base of the flow needs to be to exceed that yield strength. So higher values for yield strength represent less mobile flows, while lower values, for example, represent more mobile flows. So these are the 4 values, and really only 3, like I'll get into in just a moment, that you need to prescribe to ProDF before running a simulation. Given these model inputs, we get an output that looks something like this. So there are 2 sets of information that ProDF provides given the inputs. The first being the extent of inundation. So this is everywhere that the model predicted there to be flow greater than 10 centimeters at any point throughout the course of the simulation. So in this figure on the left, which is once again from the Montecito debris flows, everything that's colored here experienced at least 10 centimeters of flow throughout the simulation, so blue to red. In addition, however, ProDF also provides estimates of peak flow depth. So in this figure here, cooler colors represent areas of shallow flow, while warmer colors represent areas of deeper flow. And so peak flow depth is really an important thing to consider when considering hazard assessment, because deeper flows tend to have the ability to have more severe downstream impacts than shallower flows. So how do we quantify model performance? Well, if we consider the extent of inundation, we quantify model performance by comparing the modeled extent of inundation with the mapped extent of inundation. And we do so using a metric introduced by Heiser and others in 2017 that's represented here by omega sub t, which I'll refer to as the similarity index. So the similarity index is composed of 3 variables, alpha, beta, and gamma, which represent overlap between modeled and mapped inundation, model underestimation, and model overestimation, respectively. Now, the similarity index is fixed between -1, which represents a total misfit between mapped and modeled deposits, and +1, which represents a perfect fit, regardless of model domain. So an example of -1 would be if you have the model, ProDF predicts that there is no flow. There's no modeled flow. That means that it's been completely underestimated. So we have a beta value of 1 and an omega value of -1. Or you have a situation where there is modeled flow, but it is completely separate from what was mapped in the field. And then you get a gamma value of 1 and an omega value of -1. +1, on the other hand, represents, like I said, a perfect fit between the modeled and the mapped deposits. we use the similarity index to calibrate the flow mobility parameters or density, the flow mobility coefficient, and yield strength to the observed extent of inundation. So we did so by first generating 3,000 random combinations of the 3 flow mobility parameters using the Latin hypercube sampling method. And then we selected these combinations within a range for each parameter defined from the literature. And we kept volume constant. So like I said, for this event in Montecito, we had well-constrained volumes. We'll have well-constrained volumes for the other inundation scenarios I'll mention. But this is important. I'll talk about the impact of volume on model output a little later in this talk. But for the purpose of this calibration, we held the volume constant. And so we defined the best fit parameters as though that yielded the lowest misfit between the mapped and the modeled extent of inundation. So areas with less misfit will have a higher similarity index. We identify a higher similarity index with better model performance. So the combinations of the flow mobility parameters that yield the highest similarity index, we determined to be the best fit parameters. So we calibrated the model for the Montecito dataset to the entire 5 watershed dataset, as well as to each of the 5 individual basins within that dataset. However, if we look first at the entire 5 watershed dataset, we see that the best fit parameters were these following values for density, the flow resistance coefficients, and yield strength. At the moment, these values may not mean much to you, but I'll be using them in a comparative sense when we look at debris flows in northern Arizona. But the density was about 2,253 kilograms per cubic meter, flow resistance value of 18.5, and a yield strength of about 300 pascals. These parameters yielded a similarity index of about 0.04. So this is, again, on a scale of -1, which is the worst case scenario, and a +1, which is the best case scenario. Another way to look at this is to see that 70% of the mapped extent of inundation was reproduced by ProDF. So these are areas shown in blue. And we do have distinct zones of overestimation shown in gold and underestimation shown in gray, which I won't get into here, but I'm happy to answer questions about at the end. And then going back to efficiency being key for the purpose of rapid hazard assessment following wildfire, this 40 square kilometer study area with a 5-meter input DEM ran on a standard laptop computer in about 45 seconds. So we see that ProDF is capable of reproducing a complex inundation scenario over a large study area in an efficient manner. If we look at the other output produced by ProDF, the peak flow depths, we also compare the observed peak flow depths to what ProDF modeled. So again, in the day following the event, there were 317 measurements of peak flow depth made in areas that overlap with the best fit inundation extent from ProDF. So there were more measurements made, but the model didn't reproduce those areas. So we only looked at the 317 points where they overlapped, and we compared the modeled peak flow depth to the observed peak flow depth. And we did so, we found that over 80% of the values were within 1 meter of each other. More than half were within 50 centimeters, and nearly 100 points, or more than 100 points, were within 20 centimeters of the observed value. If we look at it just qualitatively speaking, we see that the color scale is the same for modeled and observed peak flow depths. So we see that areas that generally had lower peak flow depths that were observed overlap areas that had lower model peak flow depths. So like the downstream extent of Montecito Creek here, or virtually the entire Buena Vista watershed to the right here. And same with higher peak flow depths. So the areas that were observed to have the highest peak flow depths, such as the middle of Montecito Creek or the upstream extent of San Isidro Creek, were also some of the areas that had the highest predicted peak flow depths by ProDF. Going back to extent of inundation, because there is such great inundation data from this site, previous studies have also tested well-established debris flow runout models against individual watersheds. So looking at a study done by Bissett, Kearton, and others in 2019, we see that they calibrated Flow2D, a physically based model to the San Ysidro Creek watershed on a 5-meter input DEM. We see that their best simulation results in a similarity index of 0.28, again on that scale of -1 to 1. And on a 5-meter input DEM for the single watershed, the model ran in approximately 41 minutes. They also looked at Lahar Z, an empirical runout model originally developed for volcanic lahars. However, coefficients for non-volcanic debris flows were also developed. So we see that they ran both variations of Lahar Z on San Ysidro Creek, once again on a 5-meter input DEM. We see that the similarity index values for the empirical model are lower than what we observe for Flow2D. However, the runtime on the same input DEM is much faster. So we have runtimes in the order of seconds as opposed to tens of minutes. However, when we look at ProDF, which we looked at in this study, we see that using the same input DEM as what was used in Beset-Kirtan 2019, we see that the similarity index value is very similar as to what was produced by the physically based Flow2D. So a value of 0.25 as opposed to 0.28. But what we also see is that we maintain the computational efficiency as what we saw for the empirical model. So again, running on the order of seconds. We wanted to take a little bit more of a look at how the input parameters influenced model output. So we plotted the values for 3,000 simulations that we calibrated for San Ysidro Creek. So like I mentioned earlier, we calibrated to each of the 5 individual watersheds using the same methodology that I outlined earlier. And we plotted the 3 input flow mobility parameters against the output similarity index for these simulations. So we see here when we plot density against the output similarity index, we see little or no really correlation between the input and the output. We see this pattern or lack thereof in all of the other watersheds from the Montecito events, as well as that watersheds outside of Southern California. So this suggests that density really has very little impact on the model output. And in future studies, density can be held constant. We sometimes use 2,000 kilograms per meter cubed. But we don't see this lack of correlation with either the flow resistance coefficient nor the yield strength. We see here that there are values of the flow resistance coefficient and yield strength that result in better similarity index values than others. However, we do see that there's still a lot of spread, which suggests that these input parameters are not working on their own, but rather in conjunction with one another. So to explore this a little bit further, we plotted the flow resistance coefficient against the yield strength with the similarity index on the color bar. So here, warmer colors indicate better model performance and cooler colors represent worse model performance. We see that when we plot yield strength and the flow resistance coefficient against one another, we do have a very distinct nonlinear relationship between the 2 parameters that suggests that if you alter the input of one, you can, variably alter the other. So for example, a higher yield strength and a lower flow resistance coefficient yields pretty similar results to a higher flow resistance coefficient and a lower yield strength. We observe this not only in San Ysidro Creek, but at all 5 individual watersheds, as well as the entire 5 watershed data set as a whole. So you'll see that, while the relationship and the values move throughout the parameter space, we always get this nonlinear relationship, or what we fondly refer to as the red banana, in all of these simulations. And we see this outside of Southern California as well. So this suggests that you might not need to calibrate a specific value for the flow resistance coefficient and yield strength. Rather, you might be able to calibrate a range that can be applicable in a certain region. Earlier, I mentioned that we had well-constrained volumes for this scenario. However, that is not always the case. So we wanted to look at how does input volume influence model output. We're once again going back to the 3,000 simulations we used to calibrate parameters for San Ysidro Creek. But instead here, we're looking at area inundated on the color bar as opposed to the similarity index. And we're looking here at volume on the x-axis and then both of the flow mobility parameters on the y-axis. And we can see, what we can tell from this plot is that volume has a pretty, strong influence on model output. So let's say that we don't have a set volume. So what we did here is we generated 3,000 random volumes for San Ysidro Creek that ranged from half of what was observed in the field. So roughly the observed volume was 300,000 cubic meters. So we selected 3,000 random volumes from 150,000 cubic meters to 600,000 cubic meters, and we generated parameter combinations with the flow resistance coefficients and the yield strength. And we can see that if we hold the flow resistance coefficient or the yield strength constant and move across the x-axis, we see that there's a pretty large variation in area inundated depending on what the input volume is. So we see that moving across the x-axis both for the yield strength and the flow resistance coefficient. And we see a similar trend if we hold the volume constant and only alter the flow mobility parameters. We can move up the y-axis, and we see, once again, there's a decently wide range of areas inundated by the model. So this suggests that it's really important to have a well-constrained input volume before running a simulation, because the volume, in essence, acts as a third flow mobility parameter. And if you don't have any of these parameters constrained, it can be very difficult to constrain the remaining. So the volume has, at the moment, debris flow volume has an established method for predicting the input volume if you don't have a well-constrained volume. And so it's important to have that constrained so that you can then calibrate the model using the flow resistance coefficient and the yield strength. So far I've talked a lot about Southern California. However, we also do a lot of work in the Southwest United States. And as I mentioned at the top of the talk, the Southwest United States is an area that is experiencing an increase in impactful post-wildfire debris flows as the wildland-urban interface continues to grow. So we conducted a study on a watershed that burned in the 2021 flag fire just upstream of the community of Pine Lake, Arizona. We can see that it's located in Northwest Arizona, pretty close to Kingman, if anyone is familiar with the area. And following rainfall after the flag fire, there was a fairly major debris flow event that impacted infrastructure both within and at the outlet of the watershed. And so in the days following the event, we went to the study site and we mapped the extent of inundation of this debris flow. And we can see, and we also gathered information regarding the debris flow volume. We can see that in terms of both volume and area inundated, this debris flow is much smaller than those observed in Southern California, the Montecito debris flows. But we wanted to see that how the model would respond if we applied the parameters we calibrated for the 5 watershed dataset in Montecito to this extent of inundation in northern Arizona. So here is an example of the model output when we apply the Montecito flow mobility parameters and the observed volume from the flag fire to this study site. We see the observed inundation extent shown in black here, and we can see everything that's colored is the output from the model using the Montecito flow mobility parameters. We see that the model, dramatically overestimates which areas will be inundated by post-wildfire debris flows. The runout length is more than twice what we observed in the field. If this were to happen in reality, this would have damaged, 3 more downstream roads, possibly impacted more houses downstream. But this output to me suggests that the debris flows at Montecito were more mobile than what we observed at the flag fire. And so if this is the case, we would expect to see differences in the parameters calibrated for the flag fire as opposed to those calibrated for the Montecito debris flows. So applying the Montecito debris flows and just reinforcing the fact that it did not perform well, the similarity index was about negative 0.73. But what we did is we calibrated the model to the extent of inundation at the flag fire using the observed volume and the method that I outlined earlier. And we did, in fact, find that you can generate a better fit between observed extent of inundation and the modeled extent of inundation if you calibrate specifically for this site using the observed input volume. And so we established a little bit earlier that density really doesn't play much of a role in determining model output, but I used the same 3,000 randomly generated parameters for Southern California and for Northern Arizona. So we still varied density, and we found that density is off by a little bit, 2,051 kilograms per cubic meter as opposed to 2,253. The flow resistance coefficient is actually very similar between the two sites. So 18.5 for Montecito and 19.9 for this study site. This is an input range of 1 to 100. So in that scale, these are actually very close to each other. However, where we see the main difference between the two flows is in the yield strength. So the yield strength calculated for the Montecito debris flows is about 300 pascals. But the best fit yield strength for the flag fire debris flows is more than 3 times that at nearly 1,000 pascals, again, using the observed input volume. So this reinforces what I thought about the Montecito debris flows being more mobile. Like I mentioned earlier, yield strength is used to calculate stopping criteria. Higher values indicate less mobile flow. Lower values indicate more mobile flow. So this is, in fact, what we observed here. And again, similarity index when you calibrate to the observed extent of inundation at the flag fire, about 0.02 as opposed to negative 0.73. So to me, this indicates that you can't necessarily apply parameters calibrated for one region or one site to a debris flow in a different geographic and climatic region. And there are, it's the focus of future work, and still a lot of work needs to be done to determine what factors influence the best fit flow mobility parameters from site to site. Is it watershed morphology characteristics? Is it burn severity characteristics? Fine content? We're at the moment collecting as many inundation scenarios as possible, and we're calibrating to each to determine what factors may influence the mobility parameters. But one hypothesis is that differences in the content of fines may influence the flow mobility. So for example, in the Montecito debris flows, nearly 30% of the debris flow matrices were composed of clay and silt-sized particles, which in the past have hypothesized to increase flow mobility as they help raise and persist poor fluid pressures, which then in turn result in more mobile flows. And so we saw that the percent fines at the Montecito matrices were much higher than what we measured at the flag fire. So the percent fines at different matrices from the flag fire debris flow was about 11%. So a lot of future work needs to be done in identifying what influences the best fit flow mobility parameters from region to region. But to address that problem, like I said, we are calibrating the model to a wide range of inundation scenarios. So we have we have 8 burned scenarios with multiple watersheds at most sites, represented by these red dots. And we also have, although I'm not talking about unburned debris flows today, we also have 3 unburned watersheds that produce debris flows at the White Sands Missile Range in southern New Mexico. So by calibrating the model to all of these inundation extents at all these different sites, we hope to identify certain factors that are influencing or have a relationship with the best fit flow mobility parameters. That way, we hope to come up with a range of yield strength and flow resistance coefficient values that can be applied in different regions if you want to use the model in a predictive sense. Now, I just talked about what happens if you apply parameters calibrated in Southern California to parameters to a site in Northern Arizona. And we saw that that didn't work too well. But what happens if we have 2 sites that are in the same geographic region in very close proximity? So we're going to take a look at the Schultz and Pipeline fires that burned north of Flagstaff, Arizona. So the Schultz fire burned in 2010 on the eastern side of the San Francisco Peaks, just north of Flagstaff, Arizona. And, a good number of watersheds in this area produced debris flows following rainfall after the Schultz fire. We have here a picture of Ann Uberg from the Arizona Geological Survey standing next to the deposit of a debris flow that occurred following the Schultz fire. And then 12 years later, we have Anne once again standing by a debris flow deposited by the pipeline fire. So the pipeline fire burned this summer, once again on the eastern slopes of the San Francisco Peaks. It reburned a large portion of the 2010 Schultz fire. And then following rainfall, the area experienced debris flows as well. And so we are lucky enough to have both debris flow inundation extent as well as input volumes for debris flows generated by both the Schultz fire and the pipeline fire. I mean, even better, they're in watersheds right next to each other. So basin 5210, shown outlined in blue here, was burned in the 2010 Schultz fire and produced a debris flow that Anne Uberg mapped the extent of inundation and the volume of, shown in the blue circle here. So we can see that the 2010 Schultz fire produced a debris flow. And before the pipeline fire even happened, we calibrated ProDF to this extent of inundation. However, once the pipeline fire occurred and some debris flows were generated, we went up to the study site and we mapped the extent of inundation, shown here in beige, and the volume of the debris flow produced by Copeland, which is a watershed that burned in both fires. So we applied the parameters calibrated for basin 5210 to the pipeline fire using only an updated input volume. So here we see the output, the calibration for the Schultz fire basin. And so we can see the flow mobility parameters. For this particular scenario, we held the density constant. And we see that generally speaking, the combination of the flow resistance coefficient and the yield strength is similar to what we observed at the flag fire, a pretty low flow resistance coefficient and a high yield strength compared to what we saw in Southern California. And we used the observed input volume of about 5,000 cubic meters and got a similarity index of 0.06. So we can see here that blue is area where the model overlaps. I apologize for the similarity in the hillshade and the underestimation, but we can see this gray lobe here that represents model underestimation, and then gold is model overestimation. So applying these parameters calibrated for the Schultz fire to the pipeline fire debris flow, using only an updated observed volume, in this case 19,000 cubic meters, we see that the model does fairly well. Quantitatively, it produces a similarity index of 0.1, which is actually even better than what we observed at the Schultz fire deposit. But qualitatively as well, we see that it tends to reproduce what we observed in the field. So we see these two distinct snouts, and we see that it wants to deposit material on this snout to the left, and then route material down to this more distal lobe that we see to the north. So, this to me suggests that there might be some geographic or climatic features that are influencing the best fit flow mobility parameters. While we may not be able to provide or apply parameters calibrated in Southern California to sites in Northern Arizona, this suggests that if you have debris flows in the same region, if you calibrate to one watershed, you may be able to apply the model, those calibrated parameters, to in a predictive fashion or to other debris flows that you have identified in the area. So the last point I want to touch on is debris flow volume. I've talked a lot today about how most of our sites had a well-constrained debris flow volume, but I also showed that debris flow volume influences model output. So what happens if you don't have a well-constrained debris flow volume that you measured in the field, or if you want to use the model in a predictive sense? So this picture is from a fire in Southern Arizona. It doesn't have much to do, but it kind of shows how we measure volumes in the field, just using a measuring tape or a laser rangefinder to get distance, and length and azimuth of the sides of the perimeter of a deposit. So I want to take a look again at the flag fire. So this is just the same slide that I showed you earlier. The parameters that we calibrated for the flag fire, we used the observed volume here of about 1,130 cubic meters, and we get an output that looks like this. But what if we didn't have an observed volume from the field? What if a subsequent flood flow had come down and washed it away, and we had no way to estimate debris flow volume from field measurements? Well, we might want to apply the emergency assessment volume model developed by Gartner in 2014 to estimate or predict the volume that might be generated by this watershed. So it predicts the volume given peak I-15 rainfall intensity area burned at moderate to high severity, and watershed relief, with the caveat that this was developed using data from the transverse ranges of Southern California. So we applied this to our study watershed, and we ran a ProDF simulation using the parameters that we calibrated for the flag fire and the volume predicted by the emergency assessment volume model. First of all, the modeled volume was about 17 times larger than what we observed in the field. So when we applied this in conjunction with the calibrated flow mobility parameters, we got an output that looked like this. So very similar to when we applied the Thomas fire parameters, we see the runout distance is about twice as long as what we observed in the field. But more than that, we see that the modeled peak flow depth is much higher. When we applied the observed volume, we see that the peak flow depths along most of the runout path were, 10 centimeters to a meter. But applying this modeled volume, we see, a majority over a meter and large swaths of area with flow depths over 2 meters. So once again, peak flow depths have, an important role in hazard assessment. And then from the extent of inundation perspective, a similarity index of about negative 0.51. So this, I think, once again, really highlights the necessity of having a well-constrained volume. You can imagine that if we used this input volume and had to recalibrate the site, that the flow resistance and yield strength values would be much different to compensate for the more material being more mobile. So, if you want to use parameters calibrated for a site with an observed volume, but you don't have a well-constrained volume elsewhere, and you use a model that over-predicts the volume, that might result in a not great fit with what might be observed. So wrapping up, we wanted to see if that phenomenon of over-predicting the volume was isolated to the flag fire site, or if it was more widespread. So over the past several years, we've collected debris flow volume data from 17 fires across Arizona and New Mexico. We had 53 debris flow producing watersheds and 54 unique events. And we calculated the Gartner emergency assessment volume for all of these watersheds and plotted them against what we measured in the field. And we saw that the volume model established in Southern California tended to overpredict all of the watersheds, oftentimes by more than an order of magnitude, and sometimes by more than 2 orders of magnitude. This suggests that this model developed in Southern California isn't applicable elsewhere in the Southwestern United States, and that has large implications for runout modeling. Just briefly, you may notice there are some points on the x-axis here. This is because these debris flows initiated in watersheds that burned exclusively at low severity, whereas the emergency assessment model considers only areas burned at moderate and high severity. So if you plug in a 0 to the model, you get a value that doesn't exist, which I just plotted as 0. So wrapping up, why we might see differences in volume between these regions. First is sediment supply. We see a lot of dry ravel or sediment that rolls down slope into the channel under the influence of gravity following wildfire in Southern California. And these can load channels with, up to 3 meters in some cases of sediment that can then be mobilized by flow, leading to large debris flows. We just didn't see dry ravel at all at any of our sites in Arizona, New Mexico, and the upper range of debris flow volume was much larger in Southern California. For example, San Isidro Creek had a volume of 297,000 cubic meters. The largest debris flow volume I've seen in Arizona or New Mexico is 19,000 cubic meters. And even that's an outlier. I'd say 90% of our volumes are below 3,000 cubic meters in size. And then finally, triggering rainfall intensity. So rainfall intensity duration thresholds developed for Southern California and Arizona are much different. So this is the rainfall intensity needed over a 15-minute duration to trigger a debris flow. We see that value is about 19 millimeters an hour in Southern California and about triple that in northern Arizona. So you need more intense rainfall just to get a response, let alone a large debris flow. So it remains to be seen. We need to do more work to see if it's the same input parameters that affect output volume in the Southwest. And if so, we might need to calculate new coefficients for this region using the data set that we have amassed. So in conclusion, runout models are not currently a standard component of post-wildfire hazard assessments due to a lack of time and having too many parameters, but ProDF is a reduced complexity debris flow model that we found to be computationally efficient and requires only a handful of input parameters. At the moment, those flow mobility parameters need to be calibrated to each site, but we're working on determining a range of values that can be used in different regions. And volume, once again, an important input parameter that influences model output that needs to be better constrained outside of Southern California. And so, like I said, further work needs to be done to determine how the volume and flow mobility parameters vary from region to region. So with that, thank you for having me, and I would be happy to answer any questions that people may have.